All right, welcome back. Yeah, believe it or not, the local library, and the thing is, this is not local. This Libby, you should be able to get this with any library, pretty much across the United States. If you're in another country, I'm not sure what you get. Check it out. Depending on the country, you might get something. But if you're in the United States, then yeah, you basically anywhere you are, you should have access to a local library. Um, okay, so yeah, you can learn about the math for deep learning. You can learn about AI investing. Basically, the entire For Dummies series is available at mine. But anyway, this video is going to be about the Nvidia certification. So last video, I first of all, I had a career coaching session with the AI that was very helpful. That I needed that, and thank you so much to the new subscribers. I really do appreciate it. It really does help keep me going. So grateful to everyone who's subscribing. We're at the 902. I'm catching up though with the videos. I gotta start lagging behind here. Okay, so Nvidia certification, part two was the last video, and most of that unfortunately was not reading the material. It was a career coaching session with the AI, which I thought was really helpful. I really kind of urge people to use the AI in creative and novel ways, especially for ways of like personal growth that could lead to personal growth. I think it's pretty good for that. So like a good example, and maybe the next series, we'll be using the AI as a leader of an MBSR, mindfulness based stress reduction 8-week course. So you would read this, and then you would have a discussion with the AI. And I would like to do that. I thought about doing it on my personal channel, but there's nothing more valuable to a professional than stress reduction in my opinion. So I think at some point I will be doing this course as part of my professional channel for sure. I reviewed some of the material, and uh, uh, some of it is a bit triggering to me because they talk a lot about the Joshua Bell thing. If people haven't heard about that thing, basically it has to do with the classical music world, and I'm a failed classical musician, so I have like a lot of gripes about about like the classical community and kind of the pompism and the impossible expectations and the way that the audience is treated. The audience is kind of expected to behave in certain ways that most audiences are like don't know about, and then the music doesn't seem to be really played for the audience. Like the audience role in the music is almost to worship it like a deity or something, which I think is just obviously not going to catch on. I think that the classical world is growing, like because it's so much fun to like read the music, and especially like chamber, playing with friends. That is like really underrated. But um, yeah, way off topic here. Sorry about that. Okay, so yeah, so last video, what I did is I put on a stopwatch. So let's get that, and then I did the training for the amount of time that it said I could expect, and if I went over, that's fine. If I go over twice the time, then that's not fine at all. So I'm trying to keep mindful of that time, do the training that's expected of me, and then move on and get through all of this training. There's a lot to get through. There's 4 parts here, and then I'm hoping I can get through this in maybe like 2 weeks. No, and I want to take this test no longer than a month. I want to get an easy win. This is a 1-hour associate level test with 50 questions. It's cheap. It just makes so much sense, I think. I want to get this out of the way. I am definitely a candidate audience for this test. So, all right, so let's go on to the next one, which was NVIDIA NGC catalog. It should take 6 minutes. Okay, so we've got a video to watch, and then we've got some more reading here. So let's start the stopwatch.
Enterprises in every industry are adopting AI to deliver cutting-edge products and services, but they face many challenges. AI is hard, and AI workflows are complex. Data scientists and researchers need easy access to AI building blocks such as models and containers. Developers need tools to seamlessly integrate models into their API or service. And DevOps engineers need tools to deploy and manage these applications across a hybrid infrastructure. Which is why we built the NGC catalog. The NGC catalog is Nvidia's hub for GPU-optimized AI, high-performance computing, and visualization software. The catalog includes containers, deep learning models, SDKs, and Helm charts to help you start building apps quickly. Packed with the latest optimizations from Nvidia are deep learning frameworks such as TensorFlow and PyTorch get your teams up and running faster than ever before. These secure, portable, and scalable containers allow your teams to build and deploy AI apps on premises with Nvidia certified systems, in the cloud, or at the edge. State-of-the-art pre-trained models are available, ranging from conversational AI to computer vision to recommender systems. You can take these models and deploy them for inference or customize them to fit your specific use case. With our industry-specific SDKs for healthcare, robotics, smart cities and more, you can easily build and deploy high-quality applications to production. Finally, the NGC catalog offers Helm charts that let you deploy and manage your applications on Kubernetes environments.
Helm chart.
So how can all of this help you transform your business? With NGC, you can reduce costs by optimizing workflows, deliver incredible products and services faster, and decrease your overall total cost of ownership. Ready to get started? Head over to ngc.nvidia.com, or if you'd like to learn more, contact us to schedule a demo with our team.
Oh, great. I can decrease my total cost of ownership in my robotic factory where I produce whatever this product is at the scale of millions of... okay. It's not a very relatable video, but okay. Well, anyways, going on to the next part. Okay, so yeah, Nvidia NGC is a portal of enterprise services, software, and support for AI, digital twins, and high performance computing. What is NGC? And I gotta take a break. I'll be right back. All right, I'm back. So the timer hit 3. I had to take a break, so I'll start again and do another 3 minutes at least, or at most. Because okay, so Nvidia NGC is the portal of enterprise services, software management tools, and support for end-to-end AI and digital twin workflows. Bring your solutions to market faster with fully managed services, or take advantage of performance optimized software to build and deploy solutions on your preferred cloud, on-prem, and edge systems. Enterprise cloud services. NGC offers a collection of cloud services, including NVIDIA NEMO, Bio NEMO, Riva Studio for generative AI, drug discovery and speech AI solutions, and the NGC private registry for securely sharing proprietary AI software. Try state-of-the-art generative AI models from your browser. So NVIDIA Foundation Models offers an easy-to-use, interactive, and quickly an easy-to-use interface to quickly experience generative AI models from your browser without any setup. After you explore the model, you can customize it and take it to production with NVIDIA AI Enterprise. So you can try the foundation models. That would be interesting, but we want to make progress in the training. Then we've got NGC Catalog, GPU optimized software hub for AI, digital twins, and HPC. The NGC catalog provides access to GPU accelerated software that speeds up end-to-end workflows with performance optimized containers, pre-trained models, and industry-specific SDKs that can be deployed on premises, in the cloud, or at the edge. And you can explore that there. So simplify and accelerate your development. Get the optimized performance. AI framework and SDK containers are consistently optimized and released on a monthly basis to deliver a faster time solution. Pre-trained models to build AI faster. State-of-the-art pre-trained models help you build custom models faster for computer vision, speech AI, and more. Simplify with Jupyter Notebooks. Hundreds of Jupyter Notebooks let you understand, customize, test, and build models faster while taking advantage of best practices. Build with secure software. Containers undergo monthly security scans, and detailed reports are provided to ensure containers meet your company's security policy. Experience models on the fly. Test drive the models directly from your browser. Integrate them into your applications using APIs, or download and run your Windows machine without any setup. A platform for all use cases, from HPC to conversational, so high performance computing, to conversational AI, to medical imaging, to recommender systems, and more. NGC collections offer ready-to-use containers, pre-trained models, SDKs, and Helm charts for diverse use cases and industries in one place to speed up your application development and deployment process. So yeah, imagine if you could write your own recommender system. That would be really powerful, right? Because the recommender systems out there now aren't really working with you. They're kind of working against you to push things into your view that you wouldn't otherwise want to see. At least is the experience I've had. I do everything I can to turn the recommendation systems off because I've had really bad experiences with them on. So yeah, I mean, we could read all this. I don't know if we're meant to. I'm past the 6 hour mark. So I don't know. Sorry, the 6 minute mark. So I don't know what they want me to do. Do they want me to read this whole thing? Do they want me to like dive in deep with stuff? I'm just kind of confused here. Yeah, this is more than 6 minutes of stuff to read. All right, well, I gotta take another break. I'll be right back. All right, I'm back. So, yeah, you know what? Let's just close it out. So, a platform for all use cases, from HPC to conversational. Yeah, so I read that already. So, language modeling. Language modeling is a natural language processing (NLP) task that determines the probability of a given sequence of words occurring in a sentence. Recommender systems are a type of information filtering system that seeks to predict the rating or preference a user would give to an item. And I would argue not that the user would give to an item, but that whoever is paying for these recommendation systems to be integrated and developed would like a user to see. And then image segmentation. Image segmentation is the field of image processing that deals with separating an image into multiple subgroups or regions that represent distinctive objects or subparts. Then we have translation. Machine translation is the task of translating text from one language to another. All right, and I don't know. I'm just feeling really, really bad. I'm gonna try to do push-ups and see if that makes me feel better. So I'll be back. All right, I'm back. I was able to do one knee push-up, but not two, and I do not feel any better. But going on, object detection. Object detection is about not only detecting the presence and location of objects in images and videos, but also categorizing them into everyday objects. Then we've got ASR, automatic speech recognition. ASR systems include giving voice commands to an interactive tutorial assistant, converting audio to subtitles on an online interface, and more. Then text to speech synthesis, or text to speech, is the task of artificially producing human speech from raw transcripts. Text to speech models are used when a mobile device converts text on a web page to speech. Then we've got HPC, high performance computing. HPC is one of the most essential tools fueling the advancement of computational science, and that universe of scientific computing has expanded in all directions. All right, next section, supercharge your production AI, which we're way past 6 minutes now, probably 3 times over. Nvidia AI Enterprise is an end-to-end, secure, cloud-native suite of AI software that enables organizations to solve new challenges while increasing operational safety. And we're kind of a far ways off from NGC. So I feel like we're not reading about NGC anymore. Yeah, and we've got so much more to get through. So I think we finished NGC. Yeah, I think we're done with NGC. All right, so yeah, and that was more like 6 minutes. So, all right, so next is we're gonna read about the difference between AI, machine learning, and deep learning. This is the first of a multi-part series explaining the fundamentals of deep learning by longtime tech journalist Michael Copeland. Artificial intelligence is the future. Artificial intelligence is science fiction. Artificial intelligence is already part of our everyday lives and has been for a while with recommender systems. All those statements are true. It just depends on what flavor of AI you are referring to. For example, when Google's DeepMind's AlphaGo program defeated South Korean master Lee Sedol in the board game Go earlier this year, the terms AI, machine learning, and deep learning were used in the media to describe how DeepMind won. And all three are part of the reason why AlphaGo trounced Lee Sedol. But they are not the same things. The easiest way to think of their relationship is to visualize them as concentric circles with AI, the idea that came first, the largest, then machine learning, which blossomed later, and finally deep learning, which is driving today's AI explosion, fitting inside both. So really when it comes to your search term, if you want to be a part of the future, your search term should be deep learning. Because it will, it's part of that concentric circle. So that's how you. And sorry, we got the timer going here, so I don't want to inflate it. From bust to boom. Oh, and we've got a graph here as well. So yeah, they're concentric. So that means deep learning encompasses all of them. So early artificial intelligence stirs excitement in the 50s through the 80s. Then machine learning begins to flourish through the 90s and up to the 2010s. So like if you're like me and you're middle age, you might think to search for machine learning or talk a lot about machine learning if you want to really be a part of the AI boom. But for now and in the future, the what you should be saying is deep learning. Deep learning breakthroughs drive boom AI. So we can see we've got a lot of hits for that. We've got math for deep learning algorithms. That's the hands-on. So that there's, it's machine. They're still all. I don't think it's standardized the way you would think it is. Since an early flourish of optimism in the 1950s, smaller subsets of artificial intelligence, first machine learning, then deep learning, a subset of machine learning, have created ever larger disruptions. So it's a subset, right? This is a wider field. From bust to boom. AI has been part of our imaginations and simmering in research labs since a handful of computer scientists rallied around the term at the Dartmouth conferences in 1956 and birthed the field of AI. In the decades since, AI has alternatively been heralded as the key to our civilization's brightest future and tossed on technology's trash heap as a harebrained notion of overreaching heads. Frankly, until 2012, it was a bit of both. Over the past few years, AI has exploded, and especially since 2015. Much of that has to do with the wide availability of GPUs that make parallel processing even faster, cheaper, and more powerful. It also has to do with the simultaneous 1-2 punch of practically infinite storage and a flood of data at every stripe. That whole big data movement, images, text, transactions, mapping data, you name it. Let's walk through how computer scientists have moved from something of a bust until 2012 to a boom that has unleashed applications used by hundreds of millions of people every day. So, artificial intelligence, human intelligence exhibited by machines. King Me, computer programs that played checkers, were among the earliest examples of artificial intelligence, storing an early wave of excitement in the 1950s. Back in that summer of 56 conference, the dream of those AI pioneers was to construct complex machines enabled by emerging computers that possess the same characteristics of human intelligence. This is the concept we think of as general AI. Fabulous machines that have all our senses and maybe more, all our reason, and think just like we do. You've seen these machines endlessly in movies as Friend, C-3PO, and Foe, the Terminator. Although the Terminator was a friend, from what I understand. So general AI machines have remained in the movies and science fiction novels for good reason. We can't pull it off, at least not yet. What we can do falls into the concept of narrow AI. Technologies that are able to perform specific tasks as well as or better than we humans can. Examples of narrow AI are things such as image classification on a service like Pinterest and face recognition on Facebook. Those are examples of narrow AI in practice. These technologies exhibit some facets of human intelligence. But how? Where does that intelligence come from? Let us get to that get us. So there's just grammar issues in this, but it's not too bad. That gets us with an S to the next circle, machine learning. Machine learning, an approach to achieve artificial intelligence. Delete all spam messages now. So this is an example of a spam filter. Spam-free diet. Machine learning helps keep your inbox relatively free of spam. Yeah, so we're not even halfway done with the article, and we're at the time that it is. Oh, shoot. All right, so machine learning at its most basic is the practice of using algorithms to parse data, learn from it, and then make a determination or prediction about something in the world. So rather than hand coding software routines with a specific set of instructions to accomplish a particular task, the machine is trained using large amounts of data and algorithms that give it the ability to learn how to perform the task. Machine learning came directly from the minds of the early IT crowd, and the algorithmic approaches over the years included decision-free learning, inductive logic programming, clustering, reinforcement learning, and Bayesian networks, among others. As we know, none achieved the ultimate goal of general AI, and even narrow AI was mostly out of reach with early machine learning approaches. To learn more about deep learning, you can listen to a 4 to an hour long podcast, which I don't know where these numbers come from, but I don't think they're accurate. As it turned out, one of the very best application areas for machine learning for many years was computer vision. Though it still required a great deal of hand coding to get the job done, People would go in and write hand coded classifiers like edge detection filters so the program could identify where an object started and stopped, shape detection to determine if it had 8 sides, a classifier to recommend to recognize the letters stop, STOP. From all those hand coded classifiers, they would develop algorithms to make sense of the image and learn to determine whether it was a stop sign. Good, but not mind bendingly great, especially on a foggy day when the sign isn't perfectly visible or a tree obscures part of it. There's a reason computer vision and image detection didn't come close to rivaling humans until very recently. It was too brittle and too error prone. Time and the right learning algorithms made all the difference. All right, so that brings us to the last one, deep learning, a technique for implementing machine learning. Herding cats. Picking images of cats out of YouTube videos was one of the first breakthrough demonstrations of deep learning. Another algorithmic approach from the early machine learning crowd, artificial neural networks came and mostly went over the decades. Neural networks are inspired by our understanding of the biology of our brains, all those interconnections between the neurons. But unlike a biological brain where any neuron can detect to any other neuron within a certain physical distance, these artificial neural networks have discrete layers, connections, and directions of data propagation. You might, for example, take an image, chop it up into a bunch of tiles that are inputted into the first layer of the neural network. Sound check. Okay, there we go. In the first layer of individual neurons, then passes the data to a second layer. The second layer of neurons does its task, and so on, until the final layer and the final output is produced. Each neuron assigns a weighting to its input, how correct or incorrect it is relative to the task being performed. The final output is then determined by the total of those weightings. So think of our stop sign example. Attributes of a stop sign image are chopped up and examined by the neurons, its octagonal shape, its fire engine red color, its distinctive letters, its traffic sign size, and its motivation or lack thereof. The neural network's task is to conclude whether this is a stop sign or not. It comes up with a probability sector, really a highly educated guess, based on the weighting. In our example, the system might be 86% confident that the image is a stop sign, 7% confident that it's a speed limit sign, which is messed up because they're really different shapes, and 5% it's a kite stuck in a tree, and so on. And the network architecture then tells the neural network whether it is right or not. Given this example is getting ahead of itself because until recently, neural networks were all but shunned by the AI research community. They had been around since the earliest days of AI and had produced very little in the way of intelligence. The problem was even the most basic neural networks were very computationally intensive. It just wasn't a practical approach. Still, a small heretical research group led by Geoffrey Hinton at the University of Toronto kept at it, finally parallelizing the algorithms for supercomputers to run and proving the concept. But it wasn't until GPUs were deployed in the effort that the promise was realized. If we go back again to our stop sign example, and I'm now significantly over twice the amount of time that was predicted for this to take. If we go back again to our stop sign example, chances are very good that as the network is getting tuned or trained, it's coming up with wrong answers a lot. What it needs is training. It needs to see hundreds of thousands, even millions of images until the weightings of the neuron inputs are tuned so precisely that it gets the answer right practically every time. fog or no fog, rain, sun or rain, it's at that point that the neural network has taught itself what a stop sign looks like, or your mother's face in the case of Facebook, or a cat, or which is what Andrew NG did in 2012 at Google. Uh, I I think it's NIG, I guess. I don't know. Breakthrough was to take these neural networks and essentially make them huge, increase the layers and the neurons, and then run massive amounts of data through the system to train it. In NIG's case, it was images from 10 million YouTube videos. NIG put the deep in deep learning, which describes all the layers in these neural networks. Today, image recognition by machines trained via deep learning in some scenarios is better than humans, and that ranges from cats to identifying indicators for cancer in blood and tumors in MRI scans. Google's AlphaGo learned the game and trained for its Go match. It tuned its neural network by playing against itself over and over again. All right, finally almost done with this. Thanks to deep learning, AI has a bright future. Deep learning has enabled many practical applications of machine learning, and by extension, the overall field of AI. Deep learning breaks down tasks in ways that makes all kinds of machine assists seem possible, even likely. Driverless cars, better preventative healthcare, and even better movie recommendations are all here today or on the horizon. AI is the present and the future. With deep learning's help, AI may even get to that science fiction state we've so long imagined. You have a C3PO, I'll take it. You can keep your Terminator. So yeah, it's already there. Honestly, like I have a lot of really meaningful conversations with ChatGPT, and you know, as I said, like this MBSR, like who thought of that? I didn't think of that. The ChatGPT told me about this, and yeah, like I googled it, I found this course specifically, but like, you know, it's already mind blowing, and it's the worst it'll ever be. All right, so with that, it took well over twice the amount of allocated time, more like 3 times. So that's not good. This next one will take 5 minutes. You know, if you're not reading it out loud, if you're not going off topic, but that's the thing is like I feel like to really like grok something, you know, to really understand it deeply, like you have to. You know, it's like active listening, right? It's like, you know, active reading. You have to think about it. You have to reread certain parts. You have to go through it slowly. You have to like click on some of the links and look at the other parts. So it's like 5 minutes to read, you know, a scroll bar this size. Like, no, it's that's just impossible. Okay, but anyway, let's give it a shot. So what's the difference between deep learning training and inference? Editor's note, this post was updated a while ago, February 2023, more than a year ago. Schools in session. That's how to think about deep neural networks going through the training phase. Neural networks get an education for the same reason most people do, to learn to do a job. More specifically, the trained neural network is put to work out in the digital world using what it has learned to recognize images, spoken words, a blood disease, predict the next word or phrase in a sentence, or suggest the shoes someone is likely to buy next, you name it, in the streamlined form of an application. The speedier and more efficient version of a neural network infers things about new data it's presented with based on its training. In the AI lexicon, this is known as inference. All right, so deep learning consists of training and inference. Training is learning a new capability from existing data. So in order to do training, you have to have a deep learning network. You have to have a training data set to build those weights. And now your untrained neural network model is trained. And now you can do inference. You can apply this capability to new data. So you can, an app or service featuring capability can get new data that was not part of the training data set, and then it can run it through the trained model and use the functionality. Inference is where capabilities learned during deep learning training are put to work. Inference can't happen without training. Makes sense. That's how we gain and use our own knowledge for the most part. And just as we don't haul around our teachers, a few overloaded bookshelves, and a red brick schoolhouse to read a Shakespeare sonnet, inference doesn't require all the infrastructure of its training regimen to do its job well. So let's break down the progression from AI training to AI inference and how they both function. Training deep neural networks. Just as we don't haul around all our teachers, a few overloaded bookshelves, and a red brick schoolhouse to read a Shakespeare sonnet, inference doesn't require all the infrastructure of its training regimen to do its job well. While the goal is the same, knowledge, the educational process or training of a neural network is thankfully not quite like our own. Neural networks are loosely modeled on the biology of our brains, all those interconnections between the neurons. Unlike our brains, where any neuron can connect to any other neuron within a certain physical distance, artificial neural networks have separate layers, connections, and directions of data propagation. When training a neural network, training data is put into the first layer of the network, and individual neurons assigning a weighting to the input, how correct or incorrect it is, based on the task being performed. To learn more, check out Nvidia's AI inference solutions for the data center, self-driving cars, video analytics, and more. In an image recognition network, the first layer might look for edges. The next might look for how these edges form shapes, rectangles, or circles. The third might look for particular features, such as shiny eyes and button noses. Each layer passes the image to the next until the final layer and the final output determined by the total of these weightings is produced. But here's where the training differs from our own. Let's say the task was to identify images of cats. The neural network gets all these training images, does its weightings, and comes to a conclusion of cat or not. What it gets in response from the training algorithm is only right or wrong. Deep learning training is compute intensive. And if the algorithm informs the neural network that it was wrong, it doesn't get informed what the right answer is. The error is propagated back through the network's layers, and it has to guess at something else. In each attempt, it must consider other attributes. In our example, attributes of catness, and weigh the attributes examined at each layer, higher or lower. Then it guesses again and again and again until it has the correct weightings and gets the correct answer practically every time. It's a cat. Training can teach deep learning networks to correctly label images of cats in a limited set before the network is put to work detecting cats in the broader world. Now you have a data structure, and all the weights in there have been balanced based on what it has learned as you sent the training data through. It's a finely tuned thing of beauty. The problem is it's also a monster when it comes to consuming compute. For example, GPT-3 with 175 billion parameters requires roughly 300 zettaflops, which is 300,000 billion math operations across the entire training cycle. Try getting that to run on a smartphone. But that's the beauty, right? Is like, this is for training. So like after that training happens, then you can use ChatGPT on a smartphone, right? It's not like this happens for everything you do with the AI. That's where inference comes in. Congratulations, your neural network is trained and ready for inference. What you had to put in place to get your properly weighted neural network to learn, in our education analogy, all those pencils, books, teachers, dirty looks, is now way more than you need to get any specific task accomplished. Um, if anyone is going to make use of all that training in the real world, and that's the whole point, what you need is a speedy application that can retain the learning and apply it quickly to data it's never seen. That's inference, taking smaller batches of real world data and quickly coming back with the same correct answer, really prediction that something is correct. There are two main approaches to taking that hulking neural network and modifying it for speed and improved latency in applications that run across other networks. How AI inferencing works. Okay, almost there. Not quite at the double mark, so not too bad. How is inferencing used? Just turn on your smartphone. Inferencing is used to put deep learning to work for everything from speech recognition to categorizing your snapshots. The first approach looks at parts of the neural network that don't get activated after it's trained. These sections just aren't needed and can be pruned away. The second approach looks for ways to fuse multiple layers of the neural network into a single computational step. It's akin to the compression that happens to a digital image. Designers might work on these huge, beautiful, million pixel wide and tall images, but when they go to put it online, they'll turn into a JPEG. It'll be almost exactly the same, indistinguishable to the human eye, but at a smaller resolution. Similarly, with inference, you'll get almost the same accuracy of the prediction, but simplified, compressed, and optimized for runtime performance. What that means is we all use inference all the time. Your smartphone's voice activated assistant uses inference to do image search and spam filtering applications. Facebook's image recognition and Amazon's and Netflix's recommendation engines all rely on inference. GPUs, thanks to their parallel computing capabilities or ability to do many things at once, are good at both training and inference. Systems trained with GPUs allow computers to identify patterns and objects as well as, or in some cases better than, humans. And that might be on the list. After training is completed, the networks are deployed into the field for inference, classifying data to infer a result. Here too, GPUs and their parallel computing capabilities offer benefits where they run billions of computations based on the trained neural network to identify known patterns or objects. The parallel computing of GPUs also provides multi-factor speedups in traditional machine learning, using algorithms like gradient-boosted decision trees for both training and inference. You can see how these models and applications will just get smarter, faster, and more accurate. Inference will bring new applications to every aspect of our lives. It seems the same admonition. What?
Admonition.
Admonition. I was right. Act or administrating counsel. Applies to AI as it does to our youth. Don't be a fool. Stay in school. Inference awaits. So we could learn more about that by listening to an hour podcast, a half an hour podcast. But as it is, I'm pretty happy with, if I can just do everything in twice the time, that's not so bad. All right, so that was the difference between deep learning, training, and inference. Yeah. All right, so how to use GPUs for robotic development is 4 minutes, more like 8 minutes or longer, possibly even 12 minutes. I'll take a break. I'll be right back. All right, I'm back. One tip I have for people who need to do a lot of talking that I learned kind of from doing this channel is dry mouth lozenges. I use Act brand, but basically just dry mouth lozenges. And if you get it with xylitol, then it's like Biotine. I think is the major main brand. I buy like the off brand. But yeah, if you get it with xylitol, then it's like better for your mouth. Yeah. So like this is the kind I use. Oh, this is a gum. I don't recommend a gum because it's harder to talk. So like, yeah, this is exactly what I use. It's better than sipping on a glass of water for sure because it's like lasting and it makes it a lot easier to talk. So yeah, make sure that it's got xylitol because it's good for your oral health. And then yeah, it's a lot better than drinking water in my opinion. All right, so let's start the timer and then go into the next one. How to use GPUs for robotic development. Okay, so how GPUs can democratize deep reinforcement learning for robotics development. And this is a quite old article, 4 years old. And it should take 4 minutes. No, it shouldn't. It can take a puppy weeks to learn that certain kinds of behaviors will result in a yummy treat, extra cuddles, or a belly rub, and that other behaviors won't. With a system of positive reinforcement, a pet pooch will in time anticipate that chasing squirrels is less likely to be rewarded than staying by their human's side. Deep reinforcement learning, a technique used to train AI models for robotics and complex strategy problems, works off the same principle. In reinforcement learning, a software agent interacts with a real or virtual environment, relying on feedback from rewards to learn the best way to achieve its goal. Like the brain of a puppy in training, a reinforcement learning model uses information it's observed about the environment and its rewards and determines which action the agent should take next. To date, most researchers have relied on a combination of CPUs and GPUs to run reinforcement learning models. This means different parts of the computer tackle different steps of the processes, including simulating the environment, calculating rewards, choosing what action to take next, actually taking action, and then learning from the experience. But switching back and forth between CPU cores and powerful GPUs is by nature inefficient, requiring data to be transferred from one part of the system's memory to another at multiple points during the reinforcement learning training process. It's like a student who has to carry a tall stack of books and notes from classroom to classroom, plus the library before grasping a new concept. With Isaac Jim, Nvidia developers have made it possible to instead run entire reinforcement learning pipeline to run the entire reinforcement learning pipeline on GPUs, enabling significant speedups and reducing the hardware resources needed to develop these models. Here's what this breakthrough means for the deep reinforcement learning process and how much acceleration it can bring developers. Reinforcement learning on GPUs, simulation to action. When training a reinforcement learning model for a robotics task, like a humanoid robot that walks up and down stairs, it's much faster, safer, and easier to use a simulated environment than the physical world. In a simulation, developers can create a sea of virtual robots that can quickly rack up thousands of hours of experience at a task. If tested solely in the real world, a robot in training could fall down, bump into, or mishandle objects, causing potential damage to its own machinery, the object it's interacting with, or its surroundings. Testing in simulation provides the reinforcement learning model a space to practice and work out the kinks, giving it a head start when shifting to the real world. In a typical system today, the Nvidia PhysX simulation engine runs this experience gathering phase of the reinforcement learning process on Nvidia GPUs. But for other steps of the training application, developers have traditionally still used CPUs. So typical reinforcement learning today, we have two parts um, that involve GPUs and CPUs. The first part is the forward pass for simulation. So we have many simultaneous runners. We have environment simulation, so the physics and the rendering, reward and observation calculations to the rollout buffer, and then it goes through this loop here where it goes to the DNN controller, policy network, then the action output, and then I guess it gets trained in a reinforcement loop like that, and then the action output can be we got another loop like this for the rollout buffer, and then after that pass, it goes into the backward pass, which is for training. It runs periodically after many forward steps. So the rollout buffer goes into the value network, which is reinforcement learning algorithm, proximal policy optimization, and these are all GPUs. And then we've got the policy network can have another loop here, but there's a dotted line. I don't know what that dotted line means. Traditional deep reinforcement learning uses a combination of CPU and GPU computing resources, requiring significant data transfers back and forth. And this is not a 4-minute article. A key part of reinforcement learning training is conducting what's known as the forward pass. First, the system simulates the environment, records a set of observations about the state of the world, and calculates a reward for how well the agent did. The recorded observations become the input to a deep learning policy network, which chooses an action for the agent to take. Both the observations and the rewards are stored for later use in the training cycle. Finally, the action is sent back to the simulator so that the rest of the environment can be updated in response. After several rounds of these forward passes, the reinforcement learning model takes a look back, evaluating whether the actions it chose were effective or not. This information is used to update the policy network, and the cycle begins again with the improved model. GPU acceleration with Isaac Jim. To eliminate the overhead of transferring data back and forth from CPU to GPU during this reinforcement learning training cycle, Nvidia researchers have developed an approach to run every step of the process on GPUs. This is Isaac Jim, an end-to-end training environment which includes a PhysX simulation engine and a PyTorch tensor-based API. Isaac Jim makes it possible for a developer to run tens of thousands of environments simultaneously on a single GPU. That means experiments that previously required a data center with thousands of GPU cores can, in some cases, be trained on a single workstation. So we have fully accelerated reinforcement learning, and it's the same thing as it was before, but now it's all with GPUs except for the rollout buffer. So same thing, environment simulation in this loop with physics, rendering, reward, observation calculations, DNN controller, policy network, action output, going to the rollout buffer, and then down to the backward pass, the training pass, and it runs periodically after many forward steps. We get the value network, reinforcement training algorithm, proximal policy optimization, await updates periodic. So Nvidia Isaac Jim runs entire reinforcement learning pipelines on GPUs, enabling significant speedups, and we're past the double mark. And we've got a whole nother video to watch too. So decreasing the amount of hardware required makes reinforcement learning more accessible to individual researchers who don't have access to large data center resources. It can also make the process a lot faster. A simple reinforcement learning model tasked with getting a humanoid robot to walk can be trained in just a few minutes with Isaac Gym, but the impact of end-to-end GPU acceleration is more useful for more challenging tasks, like teaching a complex robot hand to manipulate a cube into a specific position. The problem requires significant dexterity by the robot and a simulation environment that involves domain randomization, a mechanism that allows the learned policy to more easily transfer to a real-world robot. Research by OpenAI tackled this task with a cluster of more than 6,000 CPU cores plus multiple Nvidia Tensor Core GPUs, and required about 30 hours of training for the reinforcement learning model to succeed at a task 20 times in a row using a feed-forward network model. Using just one Nvidia A100 GPU with Isaac Gym, Nvidia developers were able to achieve the same level of success in around 10 hours, a single GPU performing in an entire cluster by a factor of 3 times more. So to learn more about Isaac Gym, we can develop we can visit that. The video above shows a cube manipulation task trained by Isaac Gym on a single Nvidia A100 GPU and rendered in Nvidia Omniverse. So yeah, we're well over the double time, but I'm just curious. I want to watch the video, and then let's do a search for see kind of the prices. So these are still up there. You know, the RTXs are pretty affordable, but I mean, you can get it for like $5,000. So like for $5,000 at home, as long as you're using this Nvidia Isaac Gym, which I don't know what this is. Is it a product you have to pay for? Like, what is this? But if you're using it, you can do something like this. So you can teach it, you train it multiple hands to to learn how to make sure that the cube doesn't fall out of their hands. You can teach it to flip it over. So let's see how it's learning to hold it with the color side up. So now it's gonna hold it with the yellow. So it's gonna hold it with that facing forward. There we go, got it. It's gonna hold it with this facing forward. Got it. The yellow facing forward. Got it. The blue facing up. Got it. Green facing me. Got it. Blue facing up, and the white facing me. Got it. Red facing me, yellow facing forward. Got it. So like, see what it's trying to do is like it's reinforcement learning, you know, and then it's all the other ones. So only the ones that are successful are given the reward of moving forward, right? All right, so that took 12 times. Dang it. All right, so the next one would be on recommender systems. So I think that's a good stopping point. We're at about an hour. That's really kind of the most I can do. So yeah, a lot of wasting time. I am reading things out loud. I'm engaging with the material, which I think is a good thing. But man, it's not going to take like 5 minutes to read through these articles. It'll take like 3 times. But you know, if it takes 3 times, that's not bad because we got a half an hour, 45 minutes. So I should be able to finish this whole part in the next video. So, all right, stay tuned for that. Thanks to everyone subscribing. Really helps keep me motivated. And I'll see you in the next video.